Okay, what happens when you trap a laser beam inside a stream of water? I know, it sounds like something straight out of science fiction, right? But it's a real manufacturing marvel that is completely changing how we make, well, everything, from jet engines to the phone right there in your pocket. I mean, just think about that question for a second. It kind of goes against everything we think we know about fire and water. They're opposites. But what if you could combine the raw, brute force cutting power of a laser with the clean, cooling effect of a water jet? Well, as it turns out, the answer to that question solves some of the biggest problems in high-tech manufacturing today. And this comparison really says it all. Over on the left, you've got your standard dry laser. It's powerful for sure, but it's messy. It leaves behind this trail of heat damage, rough edges, you name it. But then on the right, you have the water-guided laser. It's a completely cool, clean process that delivers an unbelievably precise cut with zero mess. So what's so bad about the old way? To really appreciate just how clever this water jet idea is, you first have to understand the problem it's solving. Think of a conventional laser as a tiny controlled fire. It just burns its way through material, but that intense, overwhelming heat creates a ton of collateral damage. And that damage shows up in a few nasty ways. First, the heat creates what's called a heat-affected zone, which is really just a fancy way of saying it burns and weakens the material right next to the cut. All that heat also causes thermal stress, which can create tiny, invisible cracks that compromise the strength of the whole part. And then you've got the really messy stuff, the burrs and debris. It's basically molten gunk that splatters and then rehardens, and it all has to be cleaned off later. It works, sure, but it's not what you'd call elegant. So the solution is, well, it's just incredibly elegant. It's not about just spraying water at the cut to cool it down. Nope. Instead, the technology uses the water jet as a perfect, flexible, liquid optical fiber that literally traps the laser beam inside of it and guides it right to the target. And would you believe it? The core idea was actually discovered way back in 1841. A professor showed that you could guide light down a stream of water. But it took over 150 years and, the invention of the laser in 1960 for these two concepts to finally come together. The modern version was first developed for dentistry, of all things, before it was finally commercialized for industrial use in 1997. So the physics behind how this all works is a principle called total internal reflection, and it's the exact same reason that fiber optic cables work. Think of it like this. When the light inside the water jet hits the edge of the stream at a really shallow angle, it just can't escape. Instead of breaking out into the air, it bounces perfectly back inside. So what this means is that this ultra-smooth, perfectly steady stream of water becomes a flawless, self-repairing, and totally flexible optical fiber. The laser beam is shot into the stream right at the source, and as the water flows, that beam just bounces and bounces perfectly off the inner surface, completely trapped inside the jet. And physics even gives us the magic number. For light to stay trapped inside water as it travels into air, it has to hit that boundary at an angle greater than 48.7 degrees. As long as the machine keeps that angle wider than this critical number, the laser has absolutely no choice but to follow the water wherever it goes. Pretty cool, right? Okay, so that's the theory. But how does the actual machine pull this off? Let's pop the hood and take a look at the key components that make all this magic happen. It really all boils down to four main systems. First, obviously, you have the laser and the optics to focus it. Next, you have the water supply unit, and this is absolutely critical. It has to be an ultra-pure, perfectly stable, pulsation-free stream. Then there's a shielding gas that surrounds the water to keep that stream perfectly round and stable. And finally, the real heart of the machine, the coupling head. This is where it all comes together, perfectly injecting that laser beam right into the center of the water jet as it's formed. Now we get to the real action, right at the point of contact. This isn't just a laser with some water nearby. This is a perfectly synchronized, micro-scale dance of intense heating followed by instantaneous cooling. So here's how that dance works, step by step. First, a laser pulse zaps the material, instantly vaporizing it. This tiny explosion actually creates a plasma bubble that pushes the water away for just a split second. But as soon as that pulse ends, and we're talking nanoseconds here, that little vapor bubble collapses and the water jet slams right back down. It instantly cools the spot and flushes away every last bit of debris. It's this perfect, beautiful rhythm. Laser on, material vaporizes. Laser off, water cools and cleans. And this cycle repeats thousands, even millions of times per second,
blasting away material without ever giving heat a chance to build up and cause damage. You get all the incredible power of a laser with none of the nasty side effects.
So, what can you actually do with this incredible technology? Well, its applications are popping up in some of the most demanding industries you can imagine, where precision and material integrity are absolutely everything. Let's start with the computer chips inside all of our devices. Slicing those chips out of a silicon wafer is an incredibly delicate process. Normal lasers create tiny micro cracks that weaken them, but this clean, cool process, it results in chips that are up to 50% stronger, and that means more reliable electronics for all of us, with way fewer defects. What if you need to cut some of the hardest materials on Earth? No problem. This thing makes flawless cuts in diamonds and sapphire. And because the tool itself, the laser-filled water jet, is a perfect cylinder, it creates perfectly parallel walls on the cut, which is something that's incredibly difficult to do any other way. In the aerospace industry, every single component is beyond critical. This technology is used to drill the thousands of tiny, perfectly straight cooling holes in jet engine turbine blades. It can also cut advanced carbon fiber composites without causing delamination or burning the resin that holds it all together, a huge problem with dry lasers. And it's also perfect for tiny, intricate parts. In high-end watches, it cuts delicate little gears with a quality that's just unmatched. And for medical devices, it's a total game changer. By trapping and washing away all the debris in the water, it can safely machine toxic materials without releasing harmful dust into the air. When you step back and look at it, by combining two forces that seem like complete opposites, we've created a tool that's so much greater than the sum of its parts. It really makes you wonder, doesn't it? If we can masterfully tame fire with water to achieve this level of precision, what other impossible combinations are still out there, just waiting for us to discover them and build our future?